All right, our last topic for Unit 6 is something called empirical and molecular formulas. We're first going to learn how to calculate the empirical formula of a substance, and then we'll learn what molecular formula is and how to find it. So what an empirical formula is, it's the lowest whole number ratio of elements in a compound, okay? It's basically working backwards from percent composition. So you just took a quiz on how to find the percent composition of each element in a compound, knowing the formula. This is going backwards. If I give you the percentages, how do we figure out the formula of the compound? Okay, so it's kind of like the reverse process. So the steps are, from a given percent or from the masses of the compound, you're going to first calculate the moles of each element. So that's just a simple one-step mole conversion, mass to mole. We'll talk about what happened, how do we do empirical formula of a hydrated compound later. Okay, that's going to be our last example of the entire packet, is finding the percent, or finding the empirical formula of a hydrate. Once you have the moles of each element in the compound, you're going to divide by the smallest number of moles. Okay? Divide each thing by the smallest number of moles. That gives us our ratio of the elements to each other. Then, if necessary, we're going to multiply by a common whole number to get them to whole numbers. Okay? There's a little poem that I have here. Percent to mass, mass to mole, divide by small, multiply by whole. So a little like rhyme to help you remember how to do empirical formula. Okay? Are we almost done writing what's on the board? Percent to mass, mass to mole, divide by small, multiply by whole. And like I had said before, as to why I'm only giving you 3 example problems in your homework, is these problems do take a while, because if you notice, there's 4 steps to it. But we will eventually get to that empirical formula. Okay? And it's very methodical, just like mole conversions. All right, you ready? All right, let's look at our first example. We're going to calculate the empirical formula, which we abbreviate EF, of a compound that contains 25.9% nitrogen and 74.1% oxygen. So you might think, okay, how do I convert from percent to mass? Well, it's actually simpler than you think. You make an assumption that you have 100 grams of whatever compound you're given. So if I have 100 grams of this compound that contains nitrogen and oxygen, then I have 25.9 grams of oxygen and 74.1 grams of oxygen. I think I said oxygen first. 25.9 grams of nitrogen and 74.1 grams of oxygen. You just literally, instead of writing percent, you write grams. Okay, you can make that assumption. It is a valid assumption. So our first step is going to be converting the 25.9 grams of nitrogen to moles, and then the 74.1 grams of oxygen to moles. So this is a, like I said, one-step mole conversion. We're going to set up a little ratio, just like before. What unit's going to go on the bottom here? Grams of nitrogen. And on the top, it's going to be moles of nitrogen. Now, you might be wondering, why am I not doing N2? Well, nitrogen, yes, it is a diatomic substance. It is a diatomic element, but that only applies when nitrogen is not in a compound. It's in a compound here with oxygen. So diatomics don't apply here. Okay? If I was asking, like, if it was like a mole conversion, like, hey, what's the mass of this many moles of nitrogen gas, that would be N2. But in empirical and molecular formulas, you ignore diatomics because they don't apply because it's in a compound. So when we do the mole, when we set it up, what number goes with moles? 1. And the number that goes with grams is just whatever the atomic mass of nitrogen is on the periodic table, rounded to 2 decimal places, which is 14.01. Now let me set up the next one, and then we'll talk about sig figs with this. Okay. So for oxygen, it's going to be 74.1 grams of oxygen. Our setup for our mole conversion is going to look almost identical to the one for nitrogen, because we're doing grams to moles. So what unit will go on the top? Or what will go on the top? 1 mole of oxygen. And what's going to go on the bottom? The mass, which is 16.00 grams of oxygen. Now, when we do the division, it is actually in your best interest to take, like when you solve for the moles, carry it out to like 4 or 5 decimal places. This will avoid errors later. If you end up rounding off here for sig figs, when you divide, you could end up with some messed up numbers. So you don't have to worry about sig figs here. So you can ignore sig figs for right now. Just take it out to 4 or 5 decimal places. So when we divide 25.9 by 14.01, we're going to get the moles of nitrogen. Take it out to like 4 or 5 decimal places. What do you get? 1.84868 moles of nitrogen. And then we do the same thing for oxygen. And we get what? 4.63125 moles of oxygen. You can carry it more than 4 or 5 decimal places. I'm just giving you that hint that you want to carry a lot of decimal places. Do you have a question? Okay. I know you guys are at like the most extreme angle. These are on vision already. So if you want to pull it up on your phone so you can just see the numbers, that's fine. All right. So in our little steps, we've done percent to mass. That was just a quick, instead of writing a percent sign, we're going to write G. We've done mass to mole. Now we're going to divide by small. So which of those numbers of moles is smaller? Nitrogen's moles. So we're going to divide each by the moles of nitrogen. What is 1.84868 divided by 1.84868? 1. You're always, when you're on this step, when you're dividing by the smallest, you're always going to be comparing, you're always going to have 1 for one of them and then a number for the other. I mean, sometimes they're both 1, but because we're always comparing it back to like, okay, so for every 1 nitrogen, we're going to have so many oxygens. This is giving us how many of each atom are in the compound, right? Or the ratio of the atoms in the compound. So what do you get when you divide 4.63125 by 1.84868? It's about 2.5, about 2.5 oxygens. So this tells us that for every 1 nitrogen, there's 2.5 oxygens. So if I were to write the empirical formula from this, the numbers become the subscripts in the formula. Have you ever seen a formula that looks like that? No, you've never seen a formula with a decimal subscript. So that means we have to do the last step. We have to multiply to get them to whole numbers. Because remember, the definition of an empirical formula is the lowest whole number ratio of elements in a compound. So what can we multiply 2.5 by to make it a whole number? 2. I mean, there's many things we can multiply by, but the smallest we can multiply it by is a 2. And that would be what? 5 oxygens. Whatever we do to one, we have to do to the other. So how many nitrogens do we have? 2. 2 to 5 is the same as 1 to 2.5. The ratio stands. As long as we maintain the same ratio, we're good. So my empirical formula is N2O5. Sometimes when you do the division by the smallest number of moles, you end up getting all whole numbers and you're good. Sometimes you don't. If your number after you divide is within 0.1 of a whole number, you can round it to the whole number. If it's not, then you're going to have to end up multiplying. You typically will have either a whole number or really close to a 0.5. It might be like 0.49 or 0.51 or something like that. But you can either, you're typically going to either have whole numbers or you're going to have to multiply by 2. I make it simple for you like that. There's a problem you're going to do in 2 classes on the review day where you actually have to multiply by, like, I think it's 3. But that's like more of like a challenge type thing. Okay, on your tests and on your homework, you're either going to have whole numbers or you're going to have to multiply by 2. Okay? Let's do another problem. So we're going to determine the empirical formula for a compound that contains 36.5 grams of sodium, 25.4 grams of sulfur, and 38.1 grams of oxygen. So this one is a 3-element compound, right? And we're already at grams, so we don't have to go percent to mass. We are just starting at mass. So we have to convert our masses to what? Moles. So let's set up the mole conversion for each one and then solve it. All of these mole conversions are going to look similar, right? Because it's all grams to moles. So for all of them, what's going to be our top number in our conversion factor? 1 what? 1 mole. 1 mole of that substance. 1 mole Na, 1 mole S, 1 mole O. And the bottom will be what? The grams from the periodic table of each of those elements. Okay, the mass on the periodic table for each of those elements. Sodium has what mass on the periodic table? 22.99. What's sulfur? 32.06. And oxygen? 16.00. And remember, this is where we take it out to several decimal places so that when we divide, we hopefully get a whole number or 0.5. So how many moles of sodium do we get? No, I got what you said, 1.5876. I just rounded up to 5 because it was 4.6. If there's like individual issues here and there in a little bit, you guys are going to do a problem on your own, so I'll come around and correct them if there's individual errors. All right, what do you get for the moles of sulfur? And oxygen. All right. So now we have the moles of everything. Who has the smallest number of moles? Sulfur. So we're going to divide all of them by sulfur's moles. To get our ratio. How many sulfur atoms are in this compound? 1. Remember, something's always going to be a 1 because something's always going to be divided by itself. And for every 1 sulfur, we have how many sodiums? 2. And how many oxygens? 3. You should get 3 oxygens, or close to that number 3. Okay? Yeah. So everything's a whole number, so that's nice and easy. We don't have to multiply. We don't have to do that last step. So my empirical formula, these become the subscripts. My empirical formula is what? Na2SO3. Now, in terms of the order of the elements in the empirical formula, they're typically given to you in the problem in the order that you're going to use them or have them in the formula. But just be aware that if there's a metal in there, it's always going to be first, or typically will be first, because metals come first in ionic compounds. Okay? But if it was like a covalent compound like our last one, honestly, if the last one, if you had written it as O5N2, I'm not going to take off points because you found it correctly. Just convention says nitrogen comes first. Okay, but you guys don't have enough knowledge of why nitrogen comes first in N2O5 that I'm not going to fault you for not knowing that. But just typically, just give it to me in the order that it was given in the problem, and it'll be fine. Okay? Was there a question over here? I thought I saw your hand going up before. Okay. All right, so that's empirical formula. That's what you're doing in your homework. Let's talk about molecular formula. Molecular formula, or the MF, is not necessarily the simplest whole number ratio between atoms. The molecular formula shows the actual number of atoms in a compound. All right, before we talk about how we find the molecular formula, let me explain why it's not necessarily the lowest whole number ratio. Okay? It is possible for a compound to be the empirical formula and the molecular formula. And it is possible for it not to be. It depends on the problem. For example, C6H12O6. You should recognize that as being what? Glucose. So this is a molecular formula, I'm telling you that. In glucose, there are 6 atoms of carbon, 12 atoms of hydrogen, and 6 atoms of oxygen. Is C6H12O6 the empirical formula? No. Why not? Because what? It's not the simplest whole number ratio. You can simplify those subscripts. What would be the empirical formula of glucose? You can actually simplify it even more than that. CH2O. The empirical formula would be CH2O. If you divide all those subscripts by 6, you would get to the most reduced form. Okay, kind of like what we did with ionic compounds, we reduce down when we can. Same type of thing to get to the empirical formula. But really, in glucose, there's not just 1 carbon and 2 hydrogens and 1 oxygen. There's really 6, 12, and 6 of each of those. But the ratio is 1 to 2 to 1. All right? Let me give you another example. So C12H22O11 is the molecular formula for, does anyone know what that's called? The more common name for that? Nah, methane CH4 and butane C4H10. It's similar to glucose.
Fructose.
Not fructose, the other one.
Corn syrup.
Sucrose. What'd you say?
I don't know. Is it corn syrup?
Oh, I thought you said cornose or something like that. Cause anyway, so this is sucrose. All right, this is sucrose. That's the molecular formula for sucrose because in sucrose you have 12 carbons, 22 hydrogens, and 11 oxygens. Is that the empirical formula?
Yes.
Yes. Why? Because you can't simplify that. There's nothing you can divide all of those by to make them more simple. 11 is a prime number, so that kind of shows you that you cannot reduce those subscripts anymore. So this is also the empirical formula. Okay? So it is possible for something to be its own empirical formula, but it's also possible for it not to be, like we saw with glucose. All right? So basically, if you can reduce the formula down, it's not the empirical formula. If you can't, it is the empirical formula. So in order to find the molecular formula, like what if I didn't tell you what it was? What if you were actually having to solve for it? You would need the empirical formula. You would either need to calculate it like we just did in the previous problems, or it might just give you it like we're going to see in the next problem. Then you also need to know what is the molar mass of the molecular formula. That will be given in the problem. Okay? So once you have the empirical formula, either it's given to you or you have to find it, you have to calculate the molar mass of the empirical formula. You're going to divide the molar mass of the molecular formula over the molar mass of the empirical formula. So think M-E, M over E. Think me, M over E. Molecular over empirical. Typically, it's going to be the bigger number divided by the smaller number, but it could be the bigger number divided by itself if the empirical and molecular formulas are identical. It'll never be a smaller divided by a larger. Never. If it is, you've done something wrong. This is going to give us a multiple, which will be a whole number, that you'll distribute through to find the molecular formula. Are you ready for the example? The examples. All right. We're going to determine the molecular formula, MF, of a compound whose empirical formula is CH2O. Hey, that's also the empirical formula of glucose, isn't it? I'm going to give you a hint. The answer to this is not glucose. And the molecular mass is 120 grams per mole. So the 120 grams per mole is going to be the number we put on the top. The bottom number will be the molar mass of this. So first step is calculate the molar mass of CH2O. So go ahead and do that. There's 1 carbon, 2 hydrogens, and 1 oxygen. Yeah, round your molar mass to 2 decimal places. What do you get? 30.03 grams per mole is the molar mass of CH2O. And so we're going to do 120 divided by 30.03. And that will be a whole number multiple. If it's not really close to a whole number, you've done something wrong. Probably you found the empirical formula wrong. So that's a big red flag. And what do you get? 4. So now we're going to distribute the 4 through the empirical formula. So we're going to multiply each of the subscripts in CH2O by 4, and that will give us our molecular formula. So what is our molecular formula here? C4H8O4. Maintains the same ratio of 1 to 2 to 1, but shows the actual number of those atoms in the compound. Okay? Questions on that? All right, why don't you guys try this last one? With this one, you're going to have to determine the empirical formula first and then the molecular formula. So this is all together, going back doing, percent to mass, mass to mole, divide by small, multiply by whole, and then calculate the molar mass of it, divide it into the total molar mass, which is given in the problem, and find the molecular formula as well. All right, so when you actually calculate the empirical formula, you should get C2H5, no, not C2. Yeah, no, not H5, sorry. Now I'm all wrong. C2H5, H10O5, right? C5H10O2? This happens, I'm trying to remember it off the top of my head. C5H10O2, right? Which also is the molecular formula. All right, so when you do the math, make sure you can get to those answers. And if you can't, please ask for help, okay?